This is a presentation I gave at Las Vegas in 2014 at the International Mining Expo. The title is Holistic Modelling of Mineral Processing Plants, a Practical Approach. My name is Dr. Stephen Gay. I'm the owner of Midas Tech International, which is a new startup company. The long name of Midas is Mining Industry Data Analytics Service. We have contacts mainly in Brisbane, Queensland, but also in South Africa and India. I have an applied maths background. I worked for a number of years as an oceanographer, where I was simulating ocean currents. I then evolved from the sea to the land and carried out a PhD in mineral processing. I then worked as a researcher, primarily working on the problem of developing a holistic integrated simulator, for which the framework was achieved in 2001. I started an independent business in 2008 and then was given an opportunity to go to Canada for a number of years. After that, I went back to being independent in 2012. So I worked largely as a contractor, and then when I had spare time, I've been writing software. However, recently I've been focused primarily on the marketing of this software. There are lots of previous commercial software that I've worked on, but these days I work on my own software. Here I've listed a number of these systems. There's a VisioBow series, 1D, 2D, 3D, and then what is particularly relevant to this presentation is VisioBow 3D Plus, which estimates 3D information from 2D, and I will explain what I mean by 3D, and Visio Sim, which is a simulation system, and there are numerous sub-products which arise from the main products. I do use a Visio flowsheet and interrogate it and put it to an Access database. So that's Visio to Access. And when I use a Visio flowsheet and connect it to Excel, it's Visio to Excel. There's a general flowsheet simulator that we're currently developing in Excel called Excel Sim. In LinkedIn, you often get the question, and it's generally superficial, what is the best simulator? For which there's often responses which are one-line responses, such as you should use this simulation system or you should use another simulation system. One of my favourite quotes is, you should use such and such because it can do everything. Generally, when I respond to questions like this, I ask people what their requirements are. What are they trying to achieve? And by doing this, I've also come to grips with what I think should be in a simulator. Now, there's lots of criteria for what a simulator should have. And here I indicate what I think are most important if one wants to think of a holistic simulator. The data structure must be particle-based in order to be holistic. There had to be compatibility with other software, including my own. Simulation must be extensible, meaning that users can add their own. One must recognise that simulation is only part of a larger analysis process. Most simulation systems are originally designed for engineering design applications. Optimizing an existing plant is very different from designing a plant, and so there needed to be a simulation framework for improving the performance of an existing plant. And this is the niche market that our company is entering. There are 9 steps towards optimizing the plant. And what I'd like you to see from this slide is that simulation is only just one of those steps. So it makes no real sense to say what is the best simulator. What we really need to ask is what is the best process to improve the performance of an existing plant. Now here I've itemised the 9 steps. Understand the flow sheet, data collection, data collation, mass balancing, inference, defining operational variables, model fitting, simulating and optimizing. And we'll be going through these 9 steps in this presentation, although recognising that this presentation only goes for an hour and therefore it can only be done at a very, very superficial level. I actually did a course in mineral processing, and they run between 5 days or 6 days or 3 days. I've broken it into fundamental course and an advanced course. The fundamentals course generally includes knowledge that would be regarded as non-controversial, and in the advanced course I introduce concepts that are effectively way ahead of the status quo. There are other courses I give which are derivative courses of the simulation course. Process simulation, mass balancing, mineral processing monitoring strategies, unit models, and advanced Excel metallurgy. So I've already explained that in order to model a plant holistically, we need to use particles. And that's because particles are truly what is being processed by a mineral processing plant. Also, we need to differentiate the ore properties from the unit models. Hence, the same particle going through the same unit will have the same behaviour. Now, behaviour doesn't mean that if you put it through the same unit once, it goes through the concentrate, and the second time it must go through the concentrate. What it means is on the second time is that it has the same probability of going to the concentrate. And so we see that there is an association between behaviour and probability. More importantly, there is a strong connection between mineral processing simulation and probability theory. So here we see a multi-mineral particle. It contains a number of different minerals. So the red might be chalcopyrite and the yellow might be pyrite. Now, the floatability of this particle is affected not by how much one particular mineral is, but the distribution of all the minerals. So for complex ores, it doesn't seem very sensible to use any other data structure than multi-mineral particles. This is largely where existing mineral processing simulation systems have become stuck, because they, at best, they know how to model binary particles and they don't really know how to treat multi-mineral particles. And in the course, I provide the mathematical framework by which the extension to multi-mineral particles is not difficult. It just takes a little bit of time to understand the concept. So here are some schematic diagrams explaining the basic concepts. Large feed particles go into a ball mill and they break and they form smaller particles. In order to be able to model this, we would like to know the probability particular product particles came from particular feed particles. If we have a flotation cell, we have particles which go into the flotation cell and they have a probability of going to the concentrate or to the tails. And in this case, the red indicates the valuable mineral which is floatable. I've now explained that probability theory is fundamental to mineral processing. Most engineers are comfortable with the phenomenological type of modelling strategy, which is inclusive of semi-empirical methods. Yet that type of approach is complementary to probability modelling. Many equations used in mineral processing, combination, cyclone, flotation, also have a basis in probability theory. Yet probability theory is not taught at appropriate depth to mineral processing engineers, inclusive of chemical engineers and mechanical engineers. There is generally a poor distinction between statistics and probability theory. I would argue that many mineral processing engineers are not aware that statistical methods and probability methods are not necessarily the same. Of course, they're connected, but you can have professional statisticians and professional probabilitists. We're now just going to go a little bit deeper to understand the difference between a macro process and a microprocess. Because when we're talking about multi-mineral particles, it's quite difficult to measure these throughout the plant. And so we have to distinguish the actual process from the observations. So something that we observe, such as assay, can be considered an observable. A microprocess is a process hidden from the observer that affects the microprocess. Microprocesses do not have to be measured, but can be inferred from observable variables. Now we're going to go even further back in time, 1904, to one of my favourite applied mathematicians and theoretical physicists, Ludwig Boltzmann. Boltzmann believed in the application of probability theory to theoretical physics, and also believed that atoms formed the fundamental structure of molecules. But at the time, his theory and the theory of others about atoms was rejected by most physicists. And this meant that Ludwig Boltzmann, when he wanted to go to a physics conference in St. Louis, was not invited to present at the physics section. Rather, he was stuck in a section called Applied Mathematics. So here he believed in his methods. 100 years later, they're shown to be valid, yet at the time he was given a lot of resistance. And yet we look back and laugh at this particular problem of Ludwig Boltzmann. But here we are in mineral processing, over 100 years further than the physicists, and yet we're still not really using the correct data structure. Independently of Boltzmann, Shannon developed a theory called, at that time, communication theory, but it is since called information theory. And he used the concept of probability entropy. Shannon was a good friend of the theoretical physicist von Neumann, and there's an interesting discussion between the two. Von Neumann asked Shannon how he was getting on with his information theory, and Shannon replied, the theory was in excellent shape, except that he needed a good name for missing information. Von Neumann said to him, why don't you call it entropy? In the first place, a mathematical development, very much yours, already exists in Boltzmann's statistical mechanics. And in the second place, no one understands entropy very well, so in any discussion, you will be in a position of advantage. Now, this particular discussion is quite famous, interpretations. Many believe that Shannon shouldn't have described his equation as entropy, that it's become confusing, and others feel that doing so, he actually excessively complicated the method. Yet on the other hand, it did in fact provide the relationships between information theory and statistical mechanics, which are fundamental to statistical mechanics. However, to understand the entropy methods developed by Shannon, you don't need to understand thermodynamics, statistical mechanics, or quantum mechanics. And many people interested in information theory may in fact spend unrequired energy in understanding the theoretical physics that is a parallel subject area. Entropy evolved, and in 1951, Kullback and Leibler created the Kullback-Leibler divergence, which basically says that if we have a prior, we can use that prior as our starting point and still use entropy, so that in the absence of any information, the probability function will go to the prior. The idea of a prior is important to understand because it's not the same as an assumption. A prior is a belief in the absence of information to the contrary, and it's adjustable. The variables are adjusted from their priors to satisfy other known information, such as fixed constraints, mass balance constraints. In the absence of a prior, there's an interesting concept called an ignorant prior, which is commonly used, for which all variables are given the same value. We're now going to revisit the 9 steps, and where appropriate, look at it from a probabilistic viewpoint. Now, step 1 is flow sheeting, which really doesn't have much to do with probability theory. But many simulation systems create in-house dedicated flowsheet systems, rendering it difficult for users to use other systems. And one could argue it's an intentional commercial strategy. This means when a user performs a total simulation, many of the key 9 steps may be omitted. And so, personally, I would prefer to use a third-party flowsheet system. And so I'm specifically advocating Microsoft Visio, but there are other systems available. Microsoft Visio is at least 20 years old, and when I first discovered it, I actually went to the local electrical store, Harvey Norman, and I saw that it costs $45. These days it costs about $500 if you can get it fairly cheaply. But most mining company professional staff would already have access to Visio through Microsoft Office Professional. What many people don't know is that underneath Visio there's a language, VBA, that allows the flowsheet information to be interrogated. I use Visio and the icons have been made available by David Wiseman. Software has been created to interrogate a flowsheet, or any flowsheet, and store information in a database. And this software is called MM Visio Active. And this is an example flowsheet, which is fairly typical. Step 2, data collection. If a company doesn't collect data, then it might collect limited useful data, excessive data, or collect useful data but isn't analysing it. I have discovered that the major issue most companies would have to the 9 steps that I'm advocating would be this problem of data collection. Many companies do not collect data, at least not in a format that it's useful to identify how to improve a mineral processing plant. Step 3 is data collation. This means putting the data into an effective database system. Many mining companies and serverless groups do not have organised relational databases. Hence, in its core, they either uh, spend a lot of time doing elementary data preparation, or they simply don't bother. In the particular course, and I'm referring to the course a number of times in this seminar, I discuss ACCEPT, albeit recognising many approaches also exist for organised data storage. Many companies do not recognise the difference between an organised relational database system and a data store. And here's a fairly strong comment. I would suggest that of all the industries in the world, mineral processing, as distinct from mining and geology, uses the least public formats. That is, they like to put the data into a format which is incomprehensible to third parties. They might be motivated to do this out of confidentiality, but the reality is it makes the data analysis very difficult. And another comment is that mining companies tend to think that all they need to do is a data store, which means that they sack one of their staff members, get all this information on the computer, and put it on the server. And that's their idea of saving data. Step 4 is mass balancing. Mass balancing is a process by which observed variables are adjusted so that mass flows are consistent between feed and product. That's the primary objective. The second objective is that some unmeasured variables are estimated. And the most common unmeasured variables are solid flows and unmeasured strings. Yet, the more unmeasured variables we're trying to estimate, the harder it is to actually do. And there comes a point where the conventional approaches of mass balancing are no longer applicable. That level where we now have lots of unknown variables, those variables can be estimated by what's called plausible inference. And so we need to differentiate deductive inference from plausible inference, and we'll discuss that further. So in law courts, deductive inference is allowable, not plausible inference. So in plausible inference, there's a fairly high level of uncertainty. In my software, in the mass balancing software, the data structure is the flow of components. So if we know the multimineral particle types, it's the district flow of multimineral particles. But if it's not that, it might be the flow of the elements in each size class. This data structure is quite different to classical mass balance systems. So I actually use an information theory approach. I don't specifically use priors. The information is known, such as the observation of variables, are regarded as constraints. So in stage 1, I use an information theory approach, and I use the observations as constraints. Of course, some of the observations might be contradictory. So in stage 2, I remove the observation constraint and just let it finish iterating. And now that's a mass balance where the values have been adjusted. Now, I don't have to use the variances of the observation value. This is a common method used in mineral processing, and in general, it's very confusing because the variances are not known, yet they still put them in. However, for those users who wish to use variances, we can still use information theory. A Markov chain Monte Carlo method allows variation of observations to emulate known variances. This information theory approach means that all stages are very fast and easy to program, and algorithms are not burdened by incorporating variables. Step 5 is inference, and this is a key step that is being made available through the MIDAS-TEC software. The data structure used in MMVisioVal is a particle-based system rather than variable-based. It turns out that if sizes are measured and bulk assays are measured, MMVisioVal will still estimate the assays within sizes even if they're unmeasured. All other mass balance systems use deductive inference. This means they cannot estimate the assays within sizes if they're unmeasured. So the distinction between this software and conventional software is that it uses plausible inference. MMVisioVal 2D Plus does use the multimineral particle distributions. And so it can be used to estimate the distribution of multimineral particles in each stream. The question is, if it's using plausible inference, how certain is the estimation of these unmeasured? So how uncertain are some of these estimated variables? Some of the estimated variables may be so uncertain as to be rendered impractical, and others may be so certain as to be practical. So increased functionality has caused some general uncertainty. For a user, this is discouraging. A user is like the law court and generally does not want high uncertainty. And therefore I had to think about methodologies to improve the certainty of these unmeasured variables. And it became obvious that if I used information from different orders, it would provide me with huge advantage. And there's a provisional patent filed on this methodology. The prior for units is that the same units process the particles the same way if there are no operational changes. And if you remember, this was the fundamental concept for why we need to differentiate ore properties from unit properties. There is a surprising benefit to this methodology. Because the information from different plant orders of the same plant are now integrated, we need less measurements per order. And therefore I've put forward this idea that the methodologies advocated in this presentation can greatly reduce the cost of sampling. So the blue line indicates the traditional approach, and the red line indicates the new approach. For the same cost, we get higher accuracy, or for a given accuracy, we can do it with far less cost. There are numerous subclaims in the patent. We do not need assays of sizes, head assays and size distributions are sufficient. For coal, we do not need to estimate density distributions or washability curves. Average density for each size class is sufficient. We do not need mineralogical data, as multimineral particle distributions can be reconstructed. Does this mean we don't perform detailed sampling? So one would say that what I'm saying in the seminar is that we don't need to measure assays at the time. We don't need mineralogy. And the answer is both yes and no. Yes, because a detailed sampling campaign may not actually be required. No, because the more measurements, the better. Remember, there is uncertainty, and it allows reduction of uncertainty and better identification of problem units. But what I'm really saying is that this methodology provides a different viewpoint. Information theory provides the basis for strategic sampling. Now, there's a lot of mathematical techniques used in this approach. I'm just outlining them here for the sake of those who might have a more research bent. There's Monte Carlo simulation, Markov chain Monte Carlo, and hidden Markov models. And they won't be discussed here, however they are discussed in the course. In the following diagrams, I wish to just elucidate the methodology. The traditional approach is we have input observable OR properties, operating parameters, a unit model, and from that we estimate our output observable OR properties. And that would be fine if it worked. The trouble is that the actual mineral information is more detailed than those observable OR properties. So the only correct way to do it is to recognize that the OR properties have to be understood in depth. And here I've called that the input hidden OR property. We now apply that information to the unit model and we get the hidden output OR properties from which we can get the output observable OR properties, such as grade of mineral and recovery. Traditional approach, and this is particularly true for laboratory sampling, input observable OR properties goes to, say, a lab test, a flotation test, and we look at the outputs. And from that, we work out the properties, the kinetic rates. Another sample, model, set, output, and so forth. I'm arguing that it's far more efficient to realise that they're going into the same particular unit, and therefore the unit model, if correctly identified, is the same for each of the different samples. And so we're trying to holistically consider all the data. Step 6 is to define the operational variables. And this is where the seminar and the course gets controversial, because many models don't actually use operating variables. They are indeed very hard to implement practically. This doesn't mean they don't provide insight. But if you actually analyse where we are at with mineral processing modelling, then we're still very far behind from where we should be. Many variables used in simulating the plant are actually design variables rather than operating variables. And in the course I give, I discuss the various classic models, and I go into the variables in much greater detail than I do here. And it does indeed take about half a day to study. Users need to specify the operating variables. And so the software I've created has an operational parameter registration system. It provides a framework, and the software is customized for specific clients. Yet there may be two different staff who wish to simulate the same plant, but interested in different operating parameters. MMVisio Sim provides multiple interface capability, which is also. So here we see two particular people running a simulator, not recognizing that behind the simulator, they're actually sharing the same data. Model definition. Most models in mineral processing don't use probability theory, even though they may have originally been based on probability theory. In many instances, the historical connection with probability theory has been lost. The models don't recognize the fundamental concept that the best basis of unit behavior is that which is observed. Hence, if Rij is recovery of particle type J in size class I, and there are no changes to operating conditions, then the best model is that the recovery equals the measured recovery. This is so obvious, it's not generally stated, and as a result, in papers it's not used, and there's a lot of confusion by both researchers and operators. So the inference method allows one to identify how units are processing ore at the particle level. So models should be based on predicting changes to unit behavior. When you think about it this way, you recognize that many of the simulation books in mineral processing need to be rewritten. Because Visio DAL 2D Plus looks at how units process form, if operators record changes to operational parameters, it is then possible to more easily develop models for unit changes due to operational parameters. These models can be developed by regression. The specific approach I advocate is logistic regression to ensure recoveries are between 0 and 1, 100%. The methods in this presentation therefore advocate using the data to determine the model, rather than using imposed models, because the imposed models generally do not go to the right level of depth, and indeed aren't specifically related to the operational parameters. Hence, the method advocated here is logistic regression, which in itself is a form of machine learning. Here we see that machine learning has a particular definition, but what I want you to focus on is that machine learning is based on learning data, rather than following an explicitly programmed instruction. I'd also like to emphasize that the software, the simulation system, can use and will use models which are already available. However, when there is a lot of data, a data-driven model structure is preferred. Hence, the approach of using logistic regression is a form of machine learning. Simulation is therefore just step 8. It's the emulation of a plant by combining unit behavior to observe systematic changes caused by operational changes or feed variation. Again, different users may want to use different models. And again, the simulation system will support this ability for people to look at the same data differently. Step 9 is optimization. Engineers like to optimize a plant, but it is an overused term. In operations research, optimization means find the maximum value of the target variable, given certain constraints. The operations research concept has various alternative labels. Management science, decision science, and lately theory of constraints seem to become popular in medicine. But if we accept that given at any snapshot in time, we can't optimize a plant, because there's always uncertainty and hidden variables, we can, however, make incremental improvements. And so here in this slide, I wish to compare the incremental improvement approach versus the single detailed sampling approach. You might have a maximum profit increase of, say, 5%, and the detailed sampling will certainly improve your profit. So if someone says detailed sampling has in fact increased profitability of the plant, no argument here. But I'm suggesting that for a much less technical cost, you could have incrementally improved the plant. Maybe not as well as you could have done by detailed sampling, but then you can do a second sampling strategy, and then a third. But in the long term, the advantages of a strategic sampling method versus a detailed sampling method is that you'll get much closer to that optimum profit. And of course, there's a time advantage of this approach. If you're actually monitoring a plant monthly, daily, or hourly, this is going to be a lot more advantageous if you can make those changes over those time frames rather than the once a year campaign. That concludes what I'm going to discuss about the general process. And I'm just going to focus on inference, which is the niche capability of MIDAS. In the actual course I give numerous examples of inference and how it's a benefit. In this particular presentation, I'm giving one example only. My long-term objective is to validate inference for an entire flotation circuit. But in this talk, I just show the method for one flotation cell. The circuit I'm working on is that presented earlier, and I'm focusing just on the Rother-Kohn. The validation is largely schematic. It is a real feed and real MLA data, but I'm not doing a full I don't have full access to the company data. I take a feed and intentionally adjust the feed by increasing the respective concentrations of minerals of interest, chalcopyrite, pyrite, bornite, to create 6 different feeds. For simplicity, all particles are the same size, and I'll be doing more complex scenarios in future. I take actual MLA data and create 40 particle classes. So even though I might have 5,000 particle sections, it doesn't mean you simulate 5,000 particle sections. You only need to have particle types. So I have 4 particle types, 40 particle classes. A flotation model is applied to the ore with different floatability, hydrophobicities. So the simulation, I create the Rother-Kohn and the Rother tail, and now I want to back calculate what that flotation model was by using the feed particle distributions and the solid flows only in the column tail. The back calculation procedure knows nothing about the flotation model. Here are the different feeds, and I've highlighted where I've made adjustments in composition. And as you'll see, the ore variability is not large. Where I've increased the composition of floatable minerals, such as bornite, chalcopyrite, and pyrite, the mass percents, which is the mass percent going to the Rother-Kohn, have increased. The increases are not large. Here's an example of the particle distributions for each feed, and there's actually 40 particle classes I've only shown. And if you look at the 10th particle class, you can see it jumps quite a lot, because this is largely liberated chalcopyrite. And here's particle type 15. It has bornite, feldspar, and quartz, so it's that multi-mineral particle that is fundamental to mineral processing. The methodology of back calculation, well, I start with an ignorant prior. The probability a particle will go to the pond is a half. But I'm presuming that the model for each of the different feeds for the Rother is the same. So I adjust the prior for each order so that the pond solid flows are satisfied. I then take an average of the partition curve over these particular orders. A direct average will not develop any shape. The averaging is weighted by the respective feed, and there's mathematical reasons why one has to do that. But now I take the averages, and the unit partition curves are now the same as the average. I repeat and go back to step 1. And here's the fundamental equation for the averaging. If I only did one iteration, the results are terrible. There is no discernment of the partition curve at all. But if I use many iterations, the smart algorithm is used to make sure the algorithm iterates efficiently. And in less than 1 second CPU, although actually many iterations, we get it. And here we see the back calculated recovery of each particle type versus the actual recovery of each particle type. And the correlation is about 99%. And here we see, remember, I didn't use the mineral compositions of the cons. Here we see what's actually the actual compositions of the various minerals versus the predicted mineral composition. And you can see, again, the correspondence is very high. Again, probably about 99%. So, firstly, thank you for allowing me to give this presentation. And here are some conclusions and discussion. The particle-based structure is a real structure for modelling mineral processing plants. The particle-based structure requires advanced mathematical methods. Simulation should be seen as part of the total solution. The cost savings of applying a simulator is potentially huge. It is possible for users to develop models that can be easily integrated into a simulator. Just a comment, already existing models only need minor adjustment to be used for a particle-based structure. Now, if what I've presented interests you, there's a number of actions that can be taken. If you want to understand these concepts in detail, enroll in the course. If you would like to trial the methods explained here, mass balancing, inference, simulation, optimization, let's talk further. If you want to go ahead and increase the profitability of your mineral processing plant ASAP, then let's go. Here's a list of acknowledgements. I won't go through it in depth, but there are many people who deserve to be recognised because this is the theories developed here are based on many, many years of research.